10 hours. That is all it took. 10 hours of test observations from a telescope that had barely finished being switched on, and buried inside the light it captured were more than 2,000 objects no human being had ever seen before. Somewhere in that data, 7 of them were moving on paths close enough to Earth to matter. Nobody announced it right away. For a few days, the images everyone was looking at were just the pretty ones, glowing nebulae, sprawling galaxies, the kind of pictures that make headlines. But underneath the color and the light, something else was sitting there the whole time, waiting to be noticed. This is not science fiction, and it is not speculation. It happened in June of 2025 at an observatory perched on a mountain in Chile, using a camera larger than anything ever built for astronomy. What the machine found in its very first look at the sky is still being unpacked by researchers today, and some of what it uncovered has quietly changed how seriously astronomers are talking about the objects moving through our own solar system. Stay with this one, because the part near the end, about what still cannot be confirmed, is the part most videos on this topic leave out entirely. The Vera C. Rubin Observatory sits atop Cerro Pachon in Chile, a facility jointly funded by the National Science Foundation and the Department of Energy's Office of Science, more than 2 decades in the making. It is named for Vera Rubin, the astronomer whose work in the 1970s provided the first compelling observational evidence for dark matter, the invisible material that makes up most of the mass in the universe. On June 23, 2025, the observatory's team released its first public imagery, and along with it came a statement that framed the achievement plainly. In just over 10 hours of test observations, the observatory had already captured millions of galaxies, countless Milky Way stars, and thousands of asteroids. This was not a promotional exaggeration. It was a literal description of what the data contained, confirmed by the observatory's own leadership, including Vera Rubin of Stanford's SLAC, National Accelerator Laboratory, who called Rubin a discovery machine capable of detecting millions of changing objects every single night once its main survey begins. To understand why this matters, picture a security camera that usually watches one parking space at a time. Then imagine replacing it with a camera that can watch an entire stadium in perfect focus all at once, every single night for 10 years. That is roughly the leap Rubin represents. Its camera has a field of view about 45 times larger than the full moon as it appears in our sky, and a single image from it is so dense with detail that displaying it at full resolution would require 400 ultra-high-definition television screens lined up side by side. Now stack a second comparison on top of that. If you tried to print out just one of Rubin's images at a normal photograph size, you would need to print roughly the length of a football field just to hold all the information contained in that single frame. That is the scale of the instrument that quietly stumbled onto thousands of previously unknown objects before its official mission had even started. It helps to also picture what the camera itself looks like, because it is not some small device bolted onto a telescope tube. The LSST camera is roughly the size and weight of a small car, built with a lens more than 5 feet across, the largest ever manufactured for this kind of work. Every part of it, from the mirror design down to the sensors themselves, was engineered specifically to gather as much faint light as possible in the shortest amount of time, which is precisely the combination needed to catch something as small and dim as a distant asteroid drifting past in the dark. Here's where the story actually gets interesting, because those objects were not sitting in plain sight the way the galaxies were. Asteroids do not announce themselves in a single image. They are small, dim, and they move. Finding them requires the observatory to take repeated images of the same patch of sky and then compare them, watching for a faint point of light that shifts position while the stars around it stay fixed. Rubin's data processing system did exactly that, sorting through the noise of millions of stationary objects to isolate the ones that were quietly drifting. In doing so, during that same brief 10-hour test run, the observatory identified 2,104 asteroids that had never been catalogued before. 2,104 objects. That is not a rounding error. That is a small, previously invisible population, unmasked in less time than it takes to watch a single day pass. Now here's the part that connects to something bigger. 7 of those newly found asteroids were classified as near-Earth objects, meaning their orbits bring them into the general neighborhood of our planet. To be clear, none of the 7 pose any danger. Astronomers were quick to confirm that. But their discovery is a preview of exactly what Rubin was built to do. For comparison, roughly 20,000 new asteroids are discovered globally in an entire year by every other observatory and space-based survey combined. Rubin found more than 1/10 of that annual global total in a single test session lasting less than half a day. Once its primary 10-year mission, called the Legacy Survey of Space and Time, formally begins, scientists expect the observatory to catalog millions of new asteroids within its first 2 years alone. transforming how thoroughly we understand the population of objects sharing our solar system. It helps to slow down here and understand what the machine actually is, because the scale of it explains why this kind of discovery was even possible. Rubin's telescope uses an 8.4-meter mirror system feeding into the largest digital camera ever constructed for astronomy, officially called the LSST camera, roughly the size of a small car. That camera feeds into a data pipeline so powerful that, over its planned 10-year survey, it is expected to generate around 60 petabytes of raw information. Described by the observatory's own team as more data than everything ever written in every language throughout human history. Sandrine Thomas, the telescope and site project scientist at the observatory, called its completion an amazing achievement after decades of planning and construction. And Zeljko Ivezic, one of the astronomers central to the project, summed up the philosophy behind the entire effort. Simply, they are looking for the unknown unknowns, the things nobody has thought to search for. Yet, because the telescope is finally sensitive enough and fast enough to notice them. Let's do a quick recap before going further, because a lot has already been revealed. A brand new observatory in Chile switched on for the first time, ran a 10-hour test, and in that short window quietly detected more than 2,000 asteroids nobody had ever documented, including 7 that passed near Earth. It did this almost as a side effect while its headline images showed off sweeping views of star clusters and glowing nebulae. Now the question becomes, what else was sitting inside that same batch of test images, and how did scientists even confirm what they were looking at was real? Alongside the asteroid detections, the same release included a striking composite image of the Trifid and Lagoon nebulae, 2 star-forming clouds of gas and dust located several thousand light-years away in the direction of the constellation Sagittarius. That image alone combined 678 individual exposures, taken over roughly 7 hours of observing time, layered together to reveal faint structures in the gas that would be completely invisible in a single shot. In a separate frame, the observatory captured a section of the Virgo cluster, showing 3 galaxies caught in the act of merging alongside 2 striking spiral galaxies, all visible within the same field of view that also happened to catch drifting points of asteroid light in the foreground. Jonathan Blazik, an astrophysicist at Northeastern University, said he expected stunning views of galaxies when the images were released, and confirmed the results were genuinely extraordinary, with more than 10 million galaxies captured in that single wide-field image, representing only a small fraction of the roughly 20 billion galaxies Rubin expects to observe over its full 10-year survey. What makes this whole moment so significant is not just the number of objects found, but the method by which they were found. Rubin was not specifically designed as a dedicated asteroid hunting telescope, unlike some other facilities built purely for planetary defense. Its core mission is broader, mapping the structure of the universe, tracking dark energy and dark matter, and building an unprecedented time-lapse record of the changing sky. The asteroid discoveries emerged almost incidentally, a byproduct of the observatory's speed, its enormous field of view, and its ability to revisit the same patch of sky again and again in a single night. According to the observatory's own team, this makes Rubin one of the most effective instruments ever built for spotting fast, moving or faint objects passing through our solar system, including rare interstellar visitors that drift in from beyond our system entirely. That capability is part of why planetary defense researchers have been paying such close attention to this observatory, even though defending Earth from asteroid impacts was never its primary design goal. It's worth understanding exactly why an asteroid can hide from us for so long in the first place. Most of these objects are small, dark, and reflect very little sunlight, which means they are effectively invisible against the black backdrop of space, unless a telescope happens to be looking at precisely the right patch of sky, at precisely the right moment, with enough sensitivity to register that faint reflected light at all. Older surveys typically had to choose between a wide field of view and a fast scanning speed, rarely both. Rubin was built specifically to remove that trade-off, combining an enormous field of view with the ability to revisit the same section of sky multiple times in a single night, which is exactly the pattern needed to catch something moving. What used to take dedicated asteroid hunting programs weeks or months to piece together, Rubin appears able to do as an incidental byproduct of simply scanning the sky the way it was designed to. There's also a question worth sitting with here. If a 10-hour test run, essentially the astronomical equivalent of a dress rehearsal, could uncover thousands of previously hidden objects, what does that say about how much has simply gone unseen in the solar system until now? For decades, astronomers have worked with the assumption that the inventory of nearby asteroids was reasonably well mapped, at least for the larger, more dangerous ones. Rubin's test data quietly challenged that assumption within its first day of operation. Claire Higgs, an astronomy outreach specialist at the observatory, noted that all of the Images and underlying data are being made available to astronomers around the world, along with citizen science projects that will let members of the public help comb through the flood of information for new discoveries the software may have missed. That openness matters because a discovery this large is not really finished until independent researchers have had the chance to check it. It also means the story of what Rubin found in its first 10 hours is not really over. Every research group with access to the archive can run its own analysis, cross-check the software's classifications, and potentially catch objects the automated pipeline flagged with lower confidence, which is exactly the kind of layered verification that turns a single announcement into settled science. Now, to be honest about where things currently stand, some astronomers involved in the early review of the test data have been notably measured in their language. One researcher, when asked directly about the batch of newly found asteroids, said plainly that there were no surprises in terms of the numbers themselves, meaning the total roughly matched what modeling had predicted an instrument of Rubin's capability should find in that amount of observing time. That is worth pausing on, because it means the excitement here is not that the asteroids were unexpected in a statistical sense. It is that an unfinished, still being commissioned telescope was all ready, performing close to its designed potential before its real mission had even begun. It is also important to separate what has been confirmed from what is still being processed. The 204 asteroids and 7 near-Earth objects represent detections from that initial test run specifically, not the full output of Rubin's 10-year survey, which has not yet started in earnest. Broader claims, sometimes circulating online, suggesting the observatory has already reshaped our understanding of interstellar. Our objects, or made some dramatic discovery beyond its confirmed asteroid count, go further than the verified record currently supports. What is documented and sourced is significant enough on its own without needing embellishment. A test run, not even the real mission, outperforming expectations and hinting at just how much remains uncatalogued in our own cosmic backyard. If even a 10-hour glimpse could turn up this much, it becomes hard not to wonder what a full decade of continuous, nightly observation is going to reveal about the solar system we thought we already understood. The observatory, named after a woman who spent her career proving the universe held far more than what could initially be seen with the naked eye, now carries that same legacy forward, quite literally, inside its own physical images. Somewhere in that overwhelming wash of light and data sat thousands of small, drifting objects that had simply never been noticed before, hiding in plain sight until a machine built to look closer finally did. So here is the question worth leaving you with. Of everything covered here, which detail surprised you more? Why, that more than 2,000 asteroids were found in a single 10-hour test? Or that 7 of them turned out to be near-Earth objects that had gone completely undetected until now? Drop your answer in the comments. And if you want to see what Rubin's full 10-year survey uncovers as it unfolds, make sure you're subscribed, because this observatory has barely gotten started.